Here's a couple of new terms that we just actually talked about, but we have a name for these. Uh, the rank of T is the same thing as the dimension of the range of T. So let's say T goes from V to W, and the dimension of V is equal to N, and the dimension of W is equal to M. Then the rank is the dimension of the range, and that could get all the way up to M. No bigger, but it could get up to M, but it might be smaller. The nullity of T is the same thing as the nullity of A, if A is the matrix that represents T. So we'll just use those interchangeably. It's the dimension of the null space of T. So if the dimension of V is N, that's where the null space lives, is inside the inputs. So that that nullity could go up to N. So now we know that the rank and the nullity add up to being the dimension of the domain. So they add up to N. And it's also the same number of columns of A. It's the dimension of the V. So N. Here's some other places that we've seen rank and nullity before. Rank is the same thing as the number of pivot columns of A, and that means it's the number of linearly independent vectors in any basis of the column space of A, which is the range of T. Nullity of A is just the number of free variables in the solution to the homogeneous equation, AX equal to 0. And it's the number of linearly independent vectors in any basis of the null space of T. So we're really saying the same stuff, just to review. If the null space is thus just the 0 vector, remember the null space always has something in it, but that something might just be one vector, 0. But in that case, the dimension of the null space is nullity T is equal to 0, since 0 is not linearly independent by itself. There's no just the single vector 0 is not a linearly independent set, and so you'd say there's the size of a linear independent set is 0. So if the null space does happen to be just 0, then now we know we say the nullity is equal to 0. It's the difference between the zeros here is one is the set of the 0 vector, so all the zeros down the column, or the 0 function, whereas the nullity of T is the actual real number 0. It's the number of, it's the basis size, which is 0. Then we know already that T is 1 to 1, if that is true. And then we would know that the rank T is the whole dimension of the domain, which is N. And then, because they have to add up to N, then we would know that the columns of A are all linearly independent too, because every single one of them has to be a pivot column. If the range of T is equal to the entire codomain of T, that's when T is onto. And that's when the rank of T would turn out to be equal to the dimension of the entire codomain, which is M. And that happens when the rows of A are linearly independent. Now, if T is 1 to 1 and onto, so we call it an isomorphism, then T is invertible. That means you can find a nice linear transformation that gives you back that input for each output. And the matrix to represent T inverse is the same thing as A inverse, where A is the matrix that represents T. So for a square matrix A, that's n by n, we have a lot of stuff that's true. If the determinant of A is non-zero, then we know that A is invertible. And this is if and only if. So any one of these being true for a square matrix makes all of them true. Let's show the whole list. There, that's the list right now. So any one of these things being true makes the rest of them all true at the same time. You have determinant of A non-zero, A being invertible, so you can find the inverse. T being 1 to 1, where A is equal to the matrix representation of T. And in that case, T is also onto, because this is an n by n matrix, so the number of rows and columns is the same. And then the nullity of T has to be equal to 0, and the rank of T has to be equal to n. Then the rows of A are all linearly independent, and the columns of A are all linearly independent. Now we knew that from determinant of A not being 0 before, but now we can think of it in terms of 1 to 1 and onto. And the range of T is all of W, that's onto, and the null space of T is just 0, which is also the fact that the nullity of T is 0 number. And A of X equals 0 has one solution, 0 vector. Oh, that nullity of T should be the 0 vector too. I might fix that in the notes. And finally, T is an isomorphism because it's 1 to 1 and onto. Here's one quick example, and that is if you have T going from R3 to R3 given by T of X equals 5X. So that just means take the vector and multiply all the entries by 5. So it's a very simple linear transformation. So here's the matrix for it. If we use the standard vectors in R3, those standard vectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1. Multiply them each by 5, and then write the result in terms of the standard basis, which means that, well, the result will just look like what you get, 5, 0, 0, 0, 5, 0, and 0, 0, 5. So that's our A. And if you take the determinant, it would be 5 times 5 times 5 equals 125. So A is an isomorphism. It's interesting to note that the matrix is 5 times I. And we get all of those things true. A is 1 to 1, onto, the null space is 0, the range is all of R3, and A is invertible.